Can everybody hear me?
Yes, sir.
When I logged on, it was telling me that I was having problems with my video, or my audio rather. So, how's everybody doing?
I'm doing all right.
It is the last week of classes of this very strange semester.
It is.
You guys ready for it to all be over?
I'm very ready.
Good, I guess. All right, the first thing that I want to do today is to answer any questions that you might have about the regression assignment. Everything's going fine?
Dr. Kulinski.
Yes.
I would like you to go over your code because I found myself stuck yesterday and a couple days ago, and I cannot move forward. I
Oh yeah,
managed a couple
I got
times,
an email
but
from you, but I didn't respond. Let me go pull that email up. I spent the weekend grading for another class, so I haven't been very good over the weekend. So I'm looking at your code, at your script. Can you tell me where it begins to break down for you?
after the last line.
Oh, I tell you what. Why don't you just share? Can you share your screen with the rest of us and pull up your script?
I mean, I need to open R right now. I
Okay.
just turned on my computer, so give me a second. Okay, I will start sharing the screen.
So if we were in person, this would be the kind of live scripting sort of exercise we would do. Okay, run those lines down through line 12. All right, so read in your data, 14 and 15. Okay, so down in the output area, show me what you've got there. Okay, all right. Scroll more slowly.
Okay.
Scroll through your output. So you've got body temperatures, wall temperatures for summer, Galveston. Summer Oklahoma City, or summer Galveston. Okay, so, all right, that looks fine. So it's omitted a bunch of rows because it doesn't want to show you all that. So go show me the rest of your code starting at line 17. All right. What have you not done that you need to do?
I don't know.
Who can help him?
Change you need to filter the data.
How does he need to filter the data?
Filter it so that for what's the title? It's like you would filter it so that the condition says just summer and then the population just equals like Galveston.
But even before that, he has to filter things, because what does he have in his data file in the last column that you can see there? It was open to anybody, not just Grace. Well, okay, so in his console down there, you see that there's a number, starts with 191, 192, and 193. That's just the line number of his data file. And then in the second column, he has summer. And then what does he have in the third column?
Body temperature.
That is not body temperature that I see there. What I'm looking at is what?
That's environmental temperature.
That is
right?
environmental temperature. These are these random temperatures that we took on the wall to quantify what the environmental temperature was. So when you're running your data on this data file, you're looking at a bunch of environmental temperatures. So what does every environmental temperature not have associated with it? Athos, just give us the first 6 lines of your data file. Just anywhere, just type head and then your data file, whatever your data file is, temp. Head temp.
Where, like down?
16, like lines, put it on line 16.
Okay.
Always a good idea to look at the structure of your data. Head temp, yep. So in this data file, you have season, you have the type of temperature, you have the population, you have the body temperature, and then you have the wall temperature. Now go down to your console, look at line 200 of your console. What's in that last column, the far right column? NA, what does NA mean? See there, well, there you have a bunch of wall temperatures. Scroll down. Then you get to line, you're down there in the 190s, 200s, and you have all those NAs. Why do you not have any data in there? The NA basically means that there's none available. See all those NAs? Where do those NAs start?
130 with the GE instead of body temperature, so it's the wall temperature here? No,
No, it's
environmental.
it's a environmental temperature. So environmental temperatures don't have any gecko associated with them. They're just random temperatures on the wall. So what's the first filtering you need to do on this data set?
I gotta take the environmental temperature off.
So you can spend your time getting rid of environmental temperatures and wall temperature and all that stuff that is in this bigger data file. Or you can just filter out so that it only has what left in it.
Body temperature.
Body temperature. So one of your problems is you're trying to analyze a data set that has a bunch of stuff that isn't already in it. And I think once you filter that out, your life will then start to get much simpler.
How can I do that? Is it like that?
Well, I saw that you had some other filtering code in there in your script.
Oh yeah, but I had to HTBC. And it doesn't want to read it because I think I didn't finish this line right here. Linear hypothesis. There's something missing here.
There is something missing there, but that's not your broader issue. Your broader issue is that I think that your broader issue is that you are attempting to so what happens, so without filtering anything, so you've just got your temperature data file, run line 14.
14.
Oh, sorry, not line 14, line 21.
Line 21. Okay, so 20.
Okay, hold on. Show me the ANOVA table. Line 23. Okay, that looks right, because you should only have 182 lines of data. So even without filtering it, it's basically just ignoring all of those data that don't have a body temperature associated with a wall temperature. So in reality, you don't need to filter that. Although it would make your life a little easier to look at things if you did. So run through the rest. So forget the linear hypothesis for now. What are you doing in line? Why are you rereading your? Oh, that's body condition data. Okay, so you're reading in body condition data. So 26 and 27. Okay, so you've got it in there. So at this point, you're now filtering. All right, so run 29. Show me that data file.
It says error
Okay,
object pop not found.
so do the head of that HTBC. Yep. Leave it there so I can look at it. So go to line 29.
29
Mm-hmm.
right here.
Yep. Get rid of pop OKC. Okay, now try that.
Collection not found.
That is weird. Go up to your packages. What does he not have? Thank you. Run that. Go back down.
Okay, so I was here, right?
Yep, run that. Okay, add pop back in there now. And I think you had first pop OKC. Yep. And so there you should have a bunch of winter Oklahoma City data and nothing else if you did that correctly. Yeah, so the reason it's not filtering for you is that you didn't have tidyverse loaded. So be sure that you have the packages available. So you think that's going to fix your issue?
I mean, yes, but after all, I'm stuck here. I do this HTBC4.
Okay.
And I don't know what to do with that. I have a bunch of tables, a bunch of numbers. I don't know what to do.
Okay, so so what you're basically doing is you're doing a set of regressions. So go down, move your windows around so that your console is bigger, so that we can all see your console.
Okay, wait a second.
Yeah, just grab that thing there. Nope, make it console, not code,
Console.
not script. Go down to the bottom where it says console. Yeah, there you go. Make that bigger. Yes. Okay. So here is some standard kind of output. Go up to the top of this little output that you've got here. All right, stop. So you've run model 1 here. So what is model 1 doing an analysis of? Anybody can help us out with this. Actually, now that I'm looking more carefully at it, there's some issues with this model, isn't there?
He's checking the regression of weight as the independent variable, SVL as a dependent variable.
Yep. So I'm unplugging because I forgot my other microphone at home. Can you guys still hear me?
Yeah.
Athos, this is the model that you're testing according to your script. So we want to know how weight varies with snout vent length, not how snout vent length varies with weight. And so you've done what we talked about in class last week, which is you have listed the independent variable first and the dependent variable second. And so that's one of you're not going to get the right answer doing it this way, for one thing. So, but go back to, where did all that data come from? Go back to your output. Just run line 31 again.
31.
Run line 31 again. Sorry, 32. Now give me the output from that. Okay, so when you see the little call thing, call colon, what it's basically doing is saying you're asking, or you're calling for, from the computer program, you're calling for the computer to run this formula. And the formula is that snout vent length is determined by weight for the data in this data frame HTBC1. So one of your issues just at the beginning is that you have the order of your variables is flipped. You want to know how weight is determined by snout vent length, not how snout vent length is determined by weight. And you need to spell weight correctly. There you go. Now you're going to get a different result when you run it this way. Okay, so you see that the slope value is now different because you have flipped the models. So now do summary model 1. Okay, so somebody help us walk Athos through what this is telling you. Anybody? Are we all still here? We're all still here.
So it gives you the line of best fit. The line of best fit, the y-intercept is -4.
Okay, so this is down in the coefficient section.
Yeah.
So the coefficient section is telling you the coefficients of the linear equation line. Continue, Tom.
Okay, it's a real shallow line, and you see that by the 0.147. It's shallow but positive. So for every increase in the vent length, it gets a little bit of increase in weight.
Mainly because these are tiny geckos. They don't weigh very much to begin with.
Okay. The intercept, if you were to draw a line and go all the way back to the y-axis, it intersect at -4.
Okay, so
Uh,
the equation for the line would be weight equals negative 4.00284 plus 0.14733 times snout vent length. That's the equation of the line. What else is that telling us? Somebody else other than Tom. What else is in this output that is of use to you?
It tells you the R squared value, so just how well the regression actually fits the data.
Okay, so and what's the nature of this particular R square value? Is snout vent length is variation in snout vent length doing a good job of explaining variation in weight or not?
I mean, it accounts for a lot of it, but not all of it.
Okay, so it accounts
Like
for a lot of it, but
80%.
not, yeah, almost 80%. And in ecology, that's actually a pretty decent R square value. Anything else of value in this output here?
The F statistic and the p-value.
It's got the F statistic and the p-value. It's just the test of whether or not this slope is different from a slope of 0. And is it, Bryce?
Yeah.
Yeah, it's a slope that is significantly different from a slope of 0, and pretty significantly so. So, Athos, does that help you understand what this output is giving you?
Yeah, it helps, but it does not clarify what are the next steps for my code.
Okay, so this is the regression for Oklahoma City, because HTBC1, go up in your script window. What is HTBC1? This is the regression for winter Oklahoma City. Now, when I'm doing anything scripting wise, I almost always have a clipboard with sheets of paper or a notebook or something like this sitting next to me so that I can always take notes. So from this output, we know that the winter Oklahoma City slope is 0.1422. No, 14733, sorry. 0.14733. So your next little batch of code there, wait, what go to HTBC2.
Wait, I'm just changing one thing.
You're changing multiple things.
Yeah, it's just one thing in the all filters, the independent variable and the dependent variable, as Tom
Yep,
said.
okay, so go to line
before.
37.
Okay.
So line 37, this is winter Galveston, right? So
Yes.
filter that. There's your, you don't really need to look at it. I'm assuming that it's doing it correctly. Run model 2. Give us the output, just that one line. So here you have that winter Galveston has a slope of 0.110. So that's a different number than the slope for Oklahoma City. Is it a lower slope or is it a higher slope based on just looking at the number?
Lower.
It looks like it's lower. It looks like for each incremental rise in snout vent length, the mass of the geckos, the weight of the geckos is getting less than it is in Oklahoma City. So you can run line 41. So this just tells you more information. You also notice that the y-intercept is different. The y-intercept in this case is negative 2.79, as opposed to in the other one, it was negative 4. This is probably due to the change in slope. And so it looks like there's a difference in slope between these two things. So one of the things that you might want to know is what about these two regressions?
That they're different.
Do they differ in slope? So can somebody help Athos on how to test that?
I have a quick question.
Yeah.
So with the slope, you can tell that the snout vent length has caused the weight to go up or down.
Yes. And in this case, as snout vent length increases, the weight increases, but it increases at different rates depending on what population you're in and what time of year you're in.
So for winter gal, since the slope is 0.110,
Mhm.
that means the weight is going down.
Nope, the weight is going up.
Okay, the weight is going up.
If it was going down, what would that slope value be in terms of sign?
It would be larger. Oh, it would be negative.
It would be negative, yep.
Okay.
Okay, so okay, I have 2, I have 1, I have 2, and I have 3, and then I have 4. Okay, I have everything here. I got a bunch of slopes. What
Okay,
should I do with that?
so why did you go and do all of that while I was talking to Grace? You have two slopes right here. You have Winter Oklahoma City
What?
and you have Winter Galveston,
What
right?
what did you say before that? I'm sorry.
Why did you go through all the rest of this? I want you to stick with Winter Oklahoma City and Winter Galveston for now. So you have two slopes, right?
Okay.
One is a slope of 0.11, one is a slope of 0.14733. Can somebody help Athos with how you go about testing for whether or not these two slopes are different?
This is where you would do the linear hypothesis.
It is.
And you could say you would do it like linear hypothesis, model 2, comma, and then snout vent length. And then you would have that equal to the slope of your model 1.
That is exactly what you would do. Did you get that, Athos?
No, I heard it, but I don't know what to do.
Can you go back? Can you go back through that again, Maddie?
Yeah, so under your
there.
HTPC,
Line 23. Line
Okay.
23.
I'm here.
Yep, linear hypothesis.
okay, so change that to model 2.
Model
Nope.
1.
No,
Nope.
no. So do, yeah, model 2, comma, and then in quotations, do snout vent length.
SVL.
SVL. And then do a comma, or no, sorry, do a equals,
Inside the quotes, right?
yeah, equals,
Nope, inside the quotes.
and then type in your slope for model 1.
So
Model 1, okay.
the slope for model 1 is 0.14733.
0.1.
4733 is what I had written down. Okay, so before you go changing anything, Athos, what this is basically doing is it's testing a hypothesis. It's testing whether the data in model 2 are different from a slope of 0.14733, but that is not the slope of model 2, that's the slope of model 1. So it's asking, is the slope of the winter Oklahoma City geckos different from the slope of the winter Galveston geckos?
Okay.
Because model 2 is winter Galveston and model 1 is winter Oklahoma City, and the slope of winter Oklahoma City is 0.14733. Now, when you run that, it should then output the test for you. So run line 23.
I just did.
Oh, there it
It's
is.
right here.
And those slopes are different from one another. And it shouldn't surprise you that those slopes are different. Stop sharing your screen. I'm now going to share my screen. Because when you look at these slopes, this is winter. This is winter in Galveston. This is winter in Oklahoma City. And those slopes look different. Not only that, the slopes are such that I would have trouble envisioning fitting this slope into the confidence interval around that slope. And so, as always with statistics, the numerical result that you get should be consistent with kind of what your intuition tells you from actually looking at the data. All right, so do you understand why we did what we did there that way?
Yes. And should I do this to model 3 and 4 as well?
You should do this for all combinations of those lines.
So
I think
16
there
combinations?
I think there ends up being 6. You want to compare winter Oklahoma City with winter Galveston and summer Oklahoma City and summer Galveston. So that's 1, 2, 3. And then you want to compare winter Galveston with summer Oklahoma City and summer Galveston. That's 4 and 5. Then you want to compare summer Oklahoma City with summer Galveston. That's 6. Yeah, I think it ends up being
So I
6.
should
6
so I
different
should copy-
comparisons.
So I should copy this line and copy like that and change the model here.
So you need to think through which models are telling you what about what and which comparisons you want to make. So I'm not going to spend class time working that out for you, but you have model 1, model 2, model 3, and model 4, and you want to compare all possible combinations of those models to one another.
Okay, so 6 here. I have 3, I have 4.
So I'm gonna unplug again so I can go to my board. Here's one way of thinking about it. So this is one way of thinking about the task that you have at hand. These are the 4 things that you're wanting to compare with one another, and you want to compare all possible combinations. Winter Oklahoma City to summer Oklahoma City, winter Galveston to summer Galveston. That tells you if things change seasonally within populations. But then you also want to compare winter Galveston to winter Oklahoma City, summer Oklahoma City to summer Galveston. Tells you if the 2 populations are different within a season. And then winter Oklahoma City to summer Galveston tells you if there's this kind of interaction of the 2 things. Same thing with winter Galveston and summer Oklahoma City. So these are all possible slope comparisons that you can make. And you should make all of them. But in all cases, you have to remember which model is doing what and which slope you're comparing to which model. Okay.
I mean, okay, yeah. I was looking for something like that, as like a
Like that?
comparison of slope, yes, of course, but not
And now you
like
have the correct script language to do that.
yeah, but yeah, I was hoping to look for like a design for doing that, you know, like a structure. First you do that, second you do that, and third you do that, you know.
Yeah, you just have to write each individual line of script to do it. Each one
Yeah,
of these takes one line of script.
yeah, but yeah, I don't know where I should put the linear hypothesis together or separated.
It doesn't matter as long as you get the job done.
Okay, so I will have a linear hypothesis for module 2, module 3, module 4, and then
No,
2, 3, and 4 again.
you will have a linear hypothesis test for each of these arrows.
So just 4.
No 6. 1, 2, 3, 4, 5, 6.
Okay, I have 6 here. Can I share my screen
Sure.
to show you? Right here.
No, that is not correct. What is wrong with that?
Of course, this number here.
Yeah, so you have to be altering those numbers. So don't you're thinking about this as a scripting task, not a statistical task. You need to think about the hypotheses that you're testing. Does slope of one condition differ from slope of another condition? And so you can't just copy the code over and over and over again and then change model numbers and the slope values. You have to think about what model you're comparing to what other model. Have the first model be the model and the second thing be the second model be the slope value. So perhaps a different way of doing this would be, I use the assignment operator a number of ways when I'm scripting. And one of the ways in which I use the assignment operator is to keep myself straight. So what I might do is assign one linear hypothesis statement. And I would assign this to Winter, Oklahoma City versus Winter, Galveston. This then becomes a label so that I can remember what the freak I'm doing. And in this case, this would then be the thing that tells me what needs to go into the italics. What needs to go into the italics is whatever model I've created that is Winter, Oklahoma City. And the slope that I want to compare this to is the slope from, sorry, not slope, SVL in this case. Snout vent length is the slope of Winter, Galveston. Okay, so this then gives me a name that I can attach to this hypothesis that I'm testing, and then that name tells me what goes here and what goes here. In the same way, I probably wouldn't name these things Model 1, Model 2, Model 3, and Model 4, because I have to remember every time I want to work with these, what is Model 1? I would probably have named, so you have linear models of weight versus snout vent length. I think right now you have this for data equals model or equals HTBC1. Once again, I probably wouldn't have named this HTBC1. I probably would have given this a more descriptive model for name for my data frame, like Winter OKC or something like that. Especially it's nice because it spells the word wok. So it reminds you of stir fry and you should go eat some Asian food. And so then I would have probably assigned this something like, you know, Winter OKC. And then this would be my model name so that when I put that model up here. So think of using your assignment operator as a way of making things intuitive within your script, because right now I think you have a very non-intuitive way of going about this, calling things model 1, model 2, model 3, and model 4 that don't really help you organize the task in front of you. Does that make sense?
I mean, yes, I'm honestly kind of lost, but yeah, I'll try to do that. Is that due Wednesday?
It is due Wednesday. So just stop and sit down and think, which slopes am I supposed to be comparing to one another? You're supposed to be comparing all possible slopes. That then dictates what goes in the model category in the linear hypothesis statement and what goes in the slope value category. And I think you're capable of figuring it out. If you're not, make an appointment with me to sit down and go through it in more detail. But take a shot at figuring it out yourself first. Other questions about the project?
So we still need to also make a comparison to a slope of 1, right?
That's actually for the temperature data set. So for the temperature data set, what you want to know is, so he's been working with the body condition data set. For the temperature data set, the idea of being a thermoconformer is that your body temperature takes on the temperature of the environment around you. And so for that particular hypothesis, you're comparing those correlations between body temperature and wall temperature, not to a slope of 0. Of course, they're going to be different than a slope of 0. You're interested in whether they're different from a slope of 1.
Okay, thanks.
And so you're not going to be comparing those from model to model. You're going to be comparing each season's data by population with a slope of 1. In which case, that would just be 4 slope comparisons. 1 for winter Galveston, 1 for winter Oklahoma City, 1 for summer Galveston, 1 for summer Oklahoma City. Does that make sense?
Yeah.
Wait, I have a question about that.
Mm-hmm.
So we find the linear model for the temperature data,
Mm-hmm.
and then do we need to find the linear model for each of the like summer Galveston?
If I was analyzing this for some gecko biologist who didn't know what he was doing, I would probably give him an analysis of the entire data set unsubsetted. And then I would say, you're comparing kind of apples and oranges here, because you're looking at winter climate that is very cold, and you're looking at summer climate, which is considerably warmer. If you think about this from the standpoint of the biology of the geckos, those are 2 very different thermoregulatory environments. And so I would probably give him 2 analyses of the temperature data. One that's on the entire data set, and one that is with the data subsetted, simply out of completeness. It's up to him how he wants to present those 2 analyses, whether he wants to present both of them or only one of them when he goes to write this up for a publication. But I would probably, if I was being hired and paid as a statistician who was not being included as co-author on the paper, I would probably, for my fee, have given him everything and then let him make decisions about, which one of these analyses he wants to present. I'm going to go back to the board now, and feel free to talk to me because I have my speakers on. This guy, because he's not very sophisticated, had he done this himself, he probably would have put all of the data into one analysis. But what those data would show you is that there's a cluster of, I'm going to use different colors now. Galveston is going to be in red and Oklahoma City is going to be in blue. There is a cluster of data that are up here for Galveston in the summer, and a cluster up here that is the exact same, at the exact same place pretty much for summer Oklahoma City. So these are both summer regressions, and there's a line through there, and there's a line through there, and those lines are virtually indistinguishable from one another. But then there is a winter Galveston cluster here with a regression going through it, and there is a winter Oklahoma City down here with a cluster going through that. One of the problems, can you guys see this figure?
Yeah.
So this is wall temperature versus body temperature. One of the problems with this is that when you do a regression through this, it's going to go basically right through here. And it's kind of the equivalent of if you have two treatments and those treatments have at least interval level kinds of data associated with them. You have treatment 1 and treatment 2, and you have some response variable, some dependent variable, and one of the clusters of points is down here, and another cluster of points is up here. When you run a regression through these, it's basically linking this little cluster to this little cluster, and there's nothing in between. It's almost as if saying, if I have a single point here and a single point here, and I draw a line between them, does that line have a slope that's different from 0? This is, once again, generally a violation of normal regression practice. And that's the problem that you run into here. You don't have a continuum of data across this entire scale. You have cluster of point data here, cluster here, and cluster here. And it's more like you're drawing a line between these isolated points rather than drawing a line between continuously varying data here and continuously varying data here. Does that make sense? So what I would probably advise is for the person to evaluate each of these combinations of both season and population separately. And what you're going to find is that the geckos are more thermoconforming at some times of the year than they are at other times of the year, which shouldn't really be all that surprising to a biologist who claims to know something about the thermal biology of lizards. He should see that result and say, oh, that kind of comports with my intuition of what lizards do. Does that make sense?
So we'll be doing basically those 4 same like code sections that we did with the body condition data, and we'll do it with the temperature data.
You'll be doing those linear hypothesis statements, but in this case, you'll be testing each of those not against the slopes of one another, but you'll be comparing them with the slope of 1. Because the slope of 1 indicates that wall temperature and body temperature are the same. And so if wall temperature is 20 degrees centigrade, then you should expect gecko temperature to be 20 degrees centigrade. If geckos are thermoconforming, if their body temperature is taking on the temperature of the wall that they're on. And so you would be testing each of these slopes, not as to whether they are different from a slope of 0, you would be testing, are they different from a slope of 1? So in this case, you would have 4 slope comparisons, not 6, like you had for the body condition. So what you're doing is you're doing a ton of individual regressions, and that's good because I want you to practice regression, and this is certainly one way of doing it. Does that make sense, Grace?
Yeah, I think so.
Okay, good. All right, other questions?
Paul, back to the second part of the report.
Oh yeah, body condition?
Yeah, so we do the 6 different cross comparisons of the 4 location season combinations.
Mm-hmm.
And then we find out some of them will be different, some of them will be not different.
Yep.
Then what? How do you take that and wrap it? Where do you go from there?
Well, one of the things that you can do is I once again find tables to be useful periodically. And so I would probably throw those results into a table that makes some sense. And then I would interpret what that table means. So I think I have some of your output that you sent me via email, Tom.
Yeah, I guess just conceptually, what does it mean if the 2 slopes are different?
So
it means the geckos are long and skinny in some places and short and fat in other places, I guess.
That is exactly what it means. And so once again, one of your challenges always as a statistician who gets called in to work on data on a project that you may or may not know something about. I got called in a number of years ago by some colleagues that I work with in Puerto Rico, and they were doing a study where they really didn't have a clear idea of what their questions were at the beginning of the study. And it was about the regeneration of forests on landslides in the tropics, in places that get hit by hurricanes a lot, in really rainy hurricanes. One of the things you have to understand about hurricanes is every hurricane is somewhat different. We normally think of hurricanes as big wind events, but they also have rain associated with them. And in some cases, hurricanes are really all wind and very little rain. In some cases, there are a lot of rain and very little wind. In some cases, there are a lot of both, and in some cases, there are very little of both. And so like Hurricane Maria and Hurricane George and some of these big like Category 5 hurricanes, not only do they have high winds, but they also have a ton of rain associated with them. But there are smaller hurricanes like Hurricane Hortense, which didn't have a lot of wind associated with it, but it parked itself over Puerto Rico and like rained for 3 days straight. Huge rain effect, but very little wind effect. After Hortense came through, there were tons of landslides all throughout the mountains of Puerto Rico because of the rain element of the hurricane. One of the groups that I work with, one of the groups of people that I work with in Puerto Rico, they study landslides and the effect of landslides and how landslides revegetate. So they had these landslides that were all these different ages and all these different sizes and different slopes and on different soils. And what they were interested in what are the characteristics of a landslide that promote those landslides recovering quickly versus recovering slowly. And so they basically went out onto these landslides and they gathered like every kind of variable that you can imagine that you could measure about a landslide. The width, the length, the overall area, the slope, the type of soil that it was on, how high up in elevation it was, et cetera, et cetera, et cetera. And they had all these data and they didn't know what to do with them. And this is a classic application of multivariate techniques. And so they had all this data, they didn't know what to do with it. And so they were asking around, who can help us with this? And my postdoctoral advisor said, oh, Paul's had some graduate courses in multivariate stats. Why don't you talk to him? And so they came to me, I looked at the data, I did the analysis, I got put on the paper as a co-author simply because I did the data analysis for it. But because I'm not a landslide researcher, it's not what I do. I'm a population community ecologist. And so I had to ultimately talk a lot to them. In one case, I was doing this on a train on my way to Oregon. And me and the main author were going back and forth via email. And I finally just said, can we just talk on the phone so that we can like talk this out rather than going back and forth on email? I think it'll just be more productive. But it took me a while to wrap my head around what their vision of how landslides operate is, in order for me to make sane, sensible suggestions about the analysis, how that analysis should be done, and what that analysis ultimately means. And so when I wrote up my report of like, here's what your data mean report, I had to take what I was doing statistically, but I had to interpret it into language that they, as landslide researchers, would understand, which means that I had to learn some stuff about landslides during the process of doing that. So when you're interpreting these things in a report like this, it's good if you try and wrap your hand a little bit around what the data actually mean in the mind of the researcher as well as in the mind of the statistician. And these things, these regressions are telling you exactly that. Which populations tend to be long and thin versus long and stocky? Or are there populations and season combinations where they're also short and thin or short and stocky? In this case, they're all kind of the same length, but they differ in terms of how heavy they are per unit length. And so you really are measuring body condition. And we would generally think in natural environments as heavier means better body condition than thin, because you don't generally see many overweight geckos out there. And so if you are packing on less weight per unit length of body, that's generally a sign that you're not getting enough to eat, because we don't see geckos sitting around streaming Netflix during the pandemic getting fat on nacho cheese Doritos and pop.
Yeah.
So
a horror, they'd be watching a horror flick about giant lizards.
Yeah, perhaps. So this Galveston population, which I made reference to earlier, let me re-share my screen. And I closed that down. To share the whole screen. So this Galveston population here is generally heavier per unit length than the other seasonal population combinations, which means that those guys are just in better condition during the winter. Galveston geckos are hurting in terms of body condition. They're not only shorter, but they're also thinner as a result of that, which means that they are probably expending more energy in the winter and not eating a lot while they're expending that energy. And that's probably because during the winter, the Galveston geckos get to go dormant and conserve energy. And the Galveston geckos are at body temperatures that doesn't allow them to go dormant. But because it's winter, there's also not as much food. So in the mind of a gecko researcher, which I am a gecko researcher, I look at those things and they make biological sense to me. You, the statistician, need to tell me what those things mean numerically, statistically, but then the degree to which you can also interpret that into the biology is just going to help me understand those better. And this is also useful, Grace. So here's the body temperature data. And so this is that figure that I was just drawing up on the board. Here you have winter and summer geckos in Galveston and Oklahoma City. You see they make 1 point by themselves. Then there's another point that's lower down on the graph, both lower down in terms of body temperature and lower down in terms of wall temperature. And then there is this low cluster of points down here. And so running a regression on all of these is going to send a line right through the middle of all of this, through the middle between these two and converging on this one. But part of that is due to this big gap in here where there's very little overlap at all between the wall temperatures of winter populations and the wall temperatures of summer populations. So that's why I wouldn't advise to a researcher to do a regression on this entire data set together. I would do it mainly to show the researcher why this might not be a wise thing to do. And then I would redivert him towards what is maybe a more appropriate thing to do. And this is one of those things that I hope you guys are learning out of all of this, is that there isn't necessarily, and I've changed in my thinking about this over the years. When I was a graduate student and when I was an early faculty member, I used to think that there is one most appropriate analysis for any given data set. And I talked to my research students in that way, et cetera. I've loosened up somewhat in that there are multiple ways in many cases that you can analyze data. There are some that are more informative potentially than others, but I'm not prepared anymore to say this data set calls for this type of analysis and that's it. If you do anything other than that, you're wrong. And so I could see why a researcher might analyze this big data set all as one entity, but I can also see ways in which dividing the data up, subsetting the data up, actually tells you more about the data, and the data actually become more interesting by dividing them up rather than by leaving them all as one big lump. And it's the kind of interesting that I think a biologist working on geckos in the system would be interested in. Does that make sense?
Yeah.
Yep.
Okay.
Do we need a graph for the temperature data set and the body condition data set?
Oh my God, you need graphs for all of this, because the graphs are what's going to make the results have relevance to the person asking you for the analysis. So yes, always have some well-designed graphics. And if you're having struggles with the graphics, once again, let me know and I can talk to you about that. I have become, over the last couple of years, a big fan of faceting data. This putting the data in two categories is used using a ggplot function called facets, F-A-C-E-T-S, and I find it really useful. Let me share my, I'm still sharing my screen, aren't I? Tom sent me a thing. Tom sent me this. Let's see if I can make it bigger. This is a situation where he just graphed, this is the body condition data. He graphed all of the body condition data on one plot to kind of illustrate the differences in slopes. And I found it intriguing and informative. It's not necessarily the way I would have done it, but there's nothing wrong with doing it this way. And the nice thing about it is that it lays them all over on top of one another in a way that it's very easy to see what's different and what's not if your statistics are dictating that some of these comparisons are different slopes and some of them are not. So yeah, that would be there. So that I'm much more liberal about the way in which you graph things than I am about the way in which you do your statistics. There are lots of ways in which you can visualize your data. Some ways are going to do a better job of doing it than others. Even though this is not the way I did it originally, there's absolutely nothing wrong with this way of doing it. And in some ways, it might be actually better than doing it the way I did it originally, which is this way. And the reason that it's different, that it's better, is because these two lines in Tom's way of doing it are laid on top of these two lines, which may make that difference more apparent to the novice reader than less apparent. And so when you design graphics, always think to yourself, in what way does the graphic that I am creating communicate the actual statistical results that this graph is hoping to provide clarity about?
Dr. Kowinski,
Yeah.
regarding the writing portion of the
Mhm.
report, do you want us to go in deep or just like the methods and the results? just like the two-way ANOVA?
Nope. Methods of results and a discussion section. So don't forget the discussion section, because the discussion section is where you take the results of your analyses and you explain them to the person who's asking you to do this.
Mhm. Okay, so just like the other reports.
Just like the other reports, same kind of format. Yep.
Okay, thank you.
Back to Grace's question about graphics.
Oh, yeah.
On the first part, we're really looking to see if slopes are not equal to 1.
Yes.
And I guess maybe secondarily we're interested if it's got a good R-squared.
Mm-hmm.
But what's a good graph for doing that?
So you can, if you go to the ANCOVA example script that I've written, this one here, one of the things that you can do is you can add lines. And one of the things that you can do, if you just put a geom line in there, you can actually specify a formula for that line. So in this case, the formula is the y predicted from this model, but you could actually put in for each of those regressions a formula that basically says y equals the y-intercept for that regression times 1, plus rather, 1 times the snout vent length, and it will plot on your graph a line that is a 1-to-1 slope. And so since that's the thing that you're comparing against, that would be the thing that I would put on a graph is, I want to know, is the slope that I observe different from a 1-to-1 slope?
At the same y, starting at the same y-intercept.
Yep.
Okay, not starting at the origin.
No, and what it's going to do is it's going to plot a 1-to-1 line through whatever graph you produce.
Yeah.
Yeah.
Okay.
And so
they'd have a starting point at the y-axis.
It would start at the y-axis, but it wouldn't be the y-axis starting at 0.
Right. Yeah. Okay. Got it.
Because snout vent length only goes down to 30. So if you did this, your slope would be for temperature, your slope would start at wherever the y-axis crosses the x-axis, and it would just plot a 1-to-1 line through these points. And that's the figure actually that I would. And so each of these clusters has a different y-intercept because they're different overall body temperatures. So this would have a low y-intercept, this would have a higher y-intercept, this would have an even higher y-intercept. But from that y-intercept, you want it to plot a slope of 1. And you can do that just by putting that in the formula. And if you struggle with that, once again, drop me a line and I can help you with that coding. But that's the thing that I would plot. We are not really the researcher isn't really interested in, is the slope different from 0? He's interested in, is the slope different from 1?
Yeah. Can you have the line 259? Can you have multiple lines like that?
Oh yeah.
Like throw a couple of lines on the graph.
Yeah, you would want to make them different colors and stuff. But all of these things actually are lines in this thing. So in some cases, I've done them as geom line, and sometimes I've done them as vertical lines to show means and horizontal lines to show means. And so, yeah, you can throw as many line things on there as you want. In the same way that you can change the size of them, you can also change the color of them. And I would color code them in the same way that you're color coding everything else in your graphs.
Okay.
Now, on your figure that you sent me via email, and we're out of time, just those of you who are keeping track of time, adding those 1-to-1 lines to something like this would just overly complicate things. You would want to subset stuff before you started doing those kind of shenanigans. So, all right. We'll meet again on Wednesday. We'll begin again asking if you have any questions about this particular assignment. And then ultimately, I want to work through another example of ANCOVA before you go to town on that. I've put the analysis of covariance assignment on the Moodle site. So you can go in and start to take a look at that there. And I will see you guys on Wednesday.
All right.
All right, drop me a line if you need anything.